Most of the time, the universe feels solid. You drop something, it falls. You turn off the lights, the room goes dark. Things follow cause and effect. One thing leads to another. It's simple. But every now and then, something doesn't line up. You read about particles being in two places at once, about experiments where the outcome seems to depend on what someone decides later, about measurements that change the thing being measured. And you tell yourself, maybe that's just how the math works. Maybe it's only weird in theory. Then you look closer, and you realize it's not just theory. These are real experiments, repeated, verified, and still completely confusing. Not because we haven't studied them enough, but because no one can agree on what they actually mean. That's what this video is about. Not the surface level quantum is weird stuff, but the real paradoxes. The ones that have been around for decades and still don't have a clear answer. The ones that keep scientists up at night, because if they're true, then we might have the universe all wrong. When people hear the word paradox, they usually think of something like a logic puzzle or a brain teaser, something strange but mostly harmless. But in quantum physics, paradoxes aren't just puzzles. They point to something much deeper, a place where our understanding of reality breaks down. In classical physics, things make sense. If you throw a ball, it follows a path. If you flick a light switch, the bulb turns on. You might not know all the details like air resistance or the exact current running through the wire, but the basic logic is solid. The world behaves in a consistent, predictable way. That's how Newton's laws and later Einstein's relativity worked. Everything had a cause and effect. If something happened, there was a reason. But when scientists started looking at things on a much smaller scale, atoms, electrons, photons, they began to notice something strange. The rules didn't just get more complicated, they got weird. It wasn't that they didn't understand all the variables, it was that even with full knowledge, they couldn't predict certain outcomes. They could only calculate probabilities. That's where quantum mechanics came in. It gave us a framework to deal with this unpredictability. Instead of saying, this will happen, quantum mechanics says this might happen, with this chance. And it works. Quantum theory is one of the most accurate and successful scientific theories ever created. It powers our electronics, lasers, MRI machines, GPS satellites. Without it, modern technology wouldn't exist. But here's the problem. Even though quantum mechanics works incredibly well in practice, we still don't really understand what it means. The equations describe what particles do, but they don't tell us what those particles are or why they behave that way. And when we try to figure that out, we run into paradoxes, situations where different parts of the theory seem to contradict each other or lead to impossible conclusions. These paradoxes matter because they tell us something important. We're missing something. It's like having a phone that works perfectly, but every once in a while, the screen flashes with strange symbols you can't explain. Sure, it still calls and texts just fine, but don't you want to know why those flashes happen? That's what quantum paradoxes are. They're glitches in the story we tell ourselves about how reality works. One of the biggest issues is the idea of measurement. In quantum mechanics, a system can exist in many possible states at once, a situation called superposition. But when we measure it, we only see one outcome. That's fine from a practical standpoint. But what exactly counts as a measurement? A machine? A person? Does the universe know when it's being measured? That's where things get fuzzy. And that fuzziness leads to all sorts of confusing scenarios. Particles that seem to choose a path only after we look. Systems that seem to depend on whether someone observes them or not. In some cases, the outcome of an experiment appears to depend on decisions made after the event took place. These aren't just theoretical ideas. They come from real experiments, repeated many times. And every time, they make physicists uncomfortable, because the results challenge some of our most basic assumptions about time, space, and cause and effect. Even worse, there's no single interpretation of quantum mechanics that everyone agrees on. Some physicists believe the wave function, the mathematical object that describes a quantum system, is just a tool for calculating probabilities. Others think it represents something real. Some say particles exist in many worlds at once and split into separate realities when measured. Others believe everything is deterministic, and we just don't have all the information. And still others think consciousness itself plays a role in collapsing possibilities into a single outcome. The giants of physics felt this discomfort keenly. Richard Feynman famously quipped, "Nobody understands quantum physics," a nod to its elusive core. Niels Bohr went further. Those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. Roger Penrose, blunt as ever, declared, "Quantum mechanics makes absolutely no sense." Albert Einstein, unsettled by its implications, warned, "If it is correct, it signifies the end of physics as a science." And Erwin Schrödinger, whose own equations fueled the revolution, lamented, "I do not like it, and I am sorry I ever had anything to do with it." Together, these voices remind us that quantum mechanics isn't just a puzzle to solve. It's a mirror reflecting the limits of our grasp, a challenge we may never fully meet. For now, we measure, we marvel, and we muddle on, caught between awe and exasperation at a universe that refuses to play by our rules. These disagreements aren't just academic. They reveal how little we really know about what's going on at the deepest level of nature. Quantum paradoxes force scientists to confront that uncomfortable fact. They're like cracks in a wall. You can paint over them, but they're still there. And if you ignore them for too long, the whole structure might be less solid than it seems. That's why these paradoxes keep scientists up at night. It's not just that the answers are hard to find. It's that the questions themselves shake the foundation of how we define reality. Every paradox is a reminder that we're dealing with a universe that might not work the way we think it does. It might be incomplete. Or maybe we're asking the wrong questions entirely. And that's what makes them so powerful. Paradoxes are the universe's way of telling us you're not done yet. Before we continue, let me show you something interesting. You know how you can have a great idea, but the hardest part is actually putting it out there. You've got it all in your head, but then you start looking into websites, logos, layouts, hosting, and suddenly you're thinking, do I really have the time for all this? That's where Odoo comes in. It's not just some basic website builder, it's an all-in-one business platform that grows with you. In just 4 simple steps, your site's online and ready to go. You pick your type, industry and goal, choose your colors or add your logo, add the pages and features you need, pick a theme, done. And then it's all dragging and dropping blocks. You don't need to mess with code, you don't need to Google, how do I change this section? You just move stuff around, swap images, tweak layouts, whatever you want. The first app you choose is free for life. That means unlimited hosting, full support, and no ticking trial clock in the background. Plus, you also get a free custom domain for your first year, so your site actually looks legit from day one. So yeah, if you're trying to launch something, literally anything, Odoo just makes it easier. Click the link in the description and see how fast you can get something live. One of the strangest and most misunderstood ideas in quantum mechanics is the delayed choice quantum eraser. It's not as popular as the double slit experiment, but it's like the double slit's evil twin. Just more confusing and more unsettling the more you understand it. To get what's going on, imagine firing a single photon, a particle of light, through an apparatus where it has 2 possible paths to travel, such as mirrors or slits. If you don't measure which path it took, something bizarre happens. The photon behaves like a wave. It acts as if it traveled both paths simultaneously, creating an interference pattern, much like ripples in water overlapping when 2 stones are dropped in a pond. But if you place a detector to determine which path the photon took, the interference pattern disappears. The photon now behaves like a particle, choosing only one path. It's as if the mere act of obtaining information about its path forces it to decide on a single route, collapsing its wave-like nature. That's already strange enough, but the quantum eraser experiment takes things even further. Instead of deciding to measure the photon's path before it reaches the detector, you delay that decision until after the photon has already hit the screen. You allow it to pass through the system, register its position on the screen, and then, only afterward, choose whether to keep or erase the which path information. Here's where things get truly bizarre. If you choose to erase the path information after the fact, the interference pattern reappears, even though the photon had already hit the screen. It's as if your decision in the present is affecting what the photon did in the past. To be clear, this doesn't mean the screen physically changes. The individual photons stay where they landed. But when you analyze the data and sort the results based on whether the path information was erased or kept, two distinct patterns emerge, one with interference, one without. And what determines which pattern appears? A choice made after the event already happened. This isn't just a weird magic trick. It's a real experiment that's been repeated many times, including with photons and other particles. And every time, the results match the prediction, the presence or absence of path information, even when decided after the fact, determines whether you see wave-like or particle-like behavior. This leads to a big question. How can something that happens now affect something that's already happened? Doesn't that break causality? Well, not exactly. You can't use this setup to send information back in time. The interference pattern only shows up when you analyze large amounts of data and group the results based on how you handled the path information. You can't use it to send a message or predict what's going to happen. But still, the fact that this decision changes how the past behaves, at least statistically, is deeply unsettling. Some physicists try to explain it by saying the particle doesn't have a definite history until we ask about it. Others say the wave function contains all possibilities until the final interaction. And then there are interpretations that suggest time itself might not work the way we think it does. Maybe past, present, and future aren't separate at all, just different slices of a whole system. Or maybe what we call the past is just a record that's constantly being reshaped by what happens now. There's no consensus, but everyone agrees something is off. In the classical world, this kind of setup would be impossible. Imagine throwing a basketball through a hoop, watching it go in, and then later deciding whether or not you watched it. And somehow that choice changes the outcome. That's the level of weirdness we're dealing with here. The quantum eraser paradox doesn't give us a clean answer. Instead, it throws a wrench into everything we thought we knew about time and observation. It tells us the act of looking isn't just passive, it's active. It doesn't just reveal information. It helps decide which version of reality gets locked in. And that's not just strange, it's disturbing. Because if your present choices can affect the past, even in subtle, statistical ways, what does that say about the nature of time itself? Is the past fixed, or is it just another layer of probability waiting to be updated? In most physics experiments, we assume there's one shared reality. If something happens, it happens for everyone. If a measurement is made, everyone agrees on the result. But the Wigner's friend paradox questions that assumption. It asks something simple but deeply unsettling. What if two people observe the same event and disagree on what's real? The thought experiment was first proposed by physicist Eugene Wigner in 1961. He imagined a situation similar to Schrödinger's cat, but with a twist. Instead of a cat in a box, there's a human, Wigner's friend, inside a lab, measuring a quantum system. Let's say the system is a particle in superposition, like being spin up and spin down at the same time. Wigner's friend performs a measurement and records a definite outcome, maybe spin up. So far, so good. From the friend's perspective, the measurement has collapsed the superposition into a single result. The particle is no longer in both states. It has a value now. Reality has locked in. But now imagine Wigner himself is outside the lab and hasn't yet looked at the result. From his point of view, the lab, including his friend, is still part of a quantum system. He hasn't observed anything yet, so to him, the lab is in a superposition. The particle is in both states, and since the friend interacted with it, he's in a superposition too, having seen both spin up and spin down in different branches of the wave function. That's where the paradox kicks in. Wigner and his friend both did everything right. The friend made a proper measurement and saw a clear result. But from Wigner's perspective, that measurement hasn't happened yet. He sees the entire lab as one big, entangled system still in superposition. So who's right? One person sees a definite outcome. The other sees a cloud of possibilities. And this isn't just about who knows what, it's about what actually exists. Now, for a long time, this was just a thought experiment. People could argue that it didn't really matter because we can't actually put people into quantum superposition. But recently, physicists have found ways to test simplified versions of this scenario using particles and detectors. In 2019, a study published in Nature Communications showed that two observers could, under certain quantum setups, record different realities. These aren't opinions or misreadings. These are physical outcomes. One observer sees one result, another sees something else, and both are correct within their own version of events. This pushes us into new territory. In classical physics, there's a single objective reality. If two people disagree, at least one of them is wrong. But in quantum mechanics, that assumption might not hold. The Wigner's friend paradox suggests that reality could be observer-dependent, not just in terms of knowledge or perspective, but in terms of what actually happens. Some interpretations of quantum mechanics try to explain this by saying each observer has their own version of the universe, a private branch of reality. That fits with the many worlds interpretation, where every possible outcome happens, and each observer just experiences one branch. According to that view, Wigner's friend collapses into one version of reality, and Wigner collapses into a different one. They're both correct, but they're in different worlds, and they can't fully agree because they're no longer sharing the same reality. Other interpretations say that measurement isn't about collapsing the wave function at all. It's about updating information. Your knowledge of the system changes, but nothing physical actually collapses. This still leaves the door open for different observers to have different knowledge about the same system. But it doesn't fully solve the paradox, because at some point, those two observers are going to compare notes. And when they do, whose version wins? And this is what makes Wigner's friend so disturbing. It asks whether reality is even real in the way we usually mean it. If two observers can experience different outcomes for the same event, then what does it mean to say something happened? Can we really talk about objective events, or are we each locked in our own branch of perception? Think about how this plays out beyond the lab. Imagine two people witnessing the same event, say a coin toss. One sees heads, the other sees tails, and both are correct in their own frame of reference. Not because someone lied, not because someone misremembered, but because reality itself splits depending on who's watching. That sounds like science fiction, but Wigner's friend forces us to consider that maybe, just maybe, that's how the quantum world actually works. The scariest part is that we don't have a good way to resolve the paradox. There's no agreed-upon answer. It's not that physicists aren't smart enough, it's that the rules of quantum mechanics allow this kind of disagreement to exist. And yet we still don't fully understand why. The more we dig, the more this thought experiment challenges what we mean by reality, truth, and observation. It shows that the act of measurement isn't just about reading data. It might actually be creating the version of the universe you live in. And once that happens, someone else might be living in a totally different version right next to you, and you'd never know. Most of us grow up thinking time works in one direction. Something happens and then something else follows. You get out of bed, then brush your teeth, then go outside. You don't brush your teeth before waking up, and if you drop a glass, it shatters. It doesn't suddenly jump back together and fly into your hand. That's how time feels. One way, forward, no exceptions. But in quantum mechanics, things aren't so clear. The equations that describe how quantum systems evolve over time, like the Schrödinger equation, don't care about the direction of time. They work just as well forwards as they do backwards. This property is called time symmetry. Mathematically, it means that if you filmed a quantum process and played it in reverse, the math would still make sense. There's no built-in arrow of time in the basic laws. That might not seem like a big deal at first. You could just say, okay, the equations don't care about time, but real life clearly does. But the deeper you go, the more complicated it gets. Because some quantum experiments suggest that the outcome of an event can depend on something that hasn't happened yet. That's the idea behind retrocausality, where the future has an effect on the past. Let's look at an example that's often used to explain this. The delayed choice quantum eraser, which we covered earlier. In that setup, the behavior of a particle seems to depend on whether you choose to erase or keep certain information, after the particle has already gone through the system. From our everyday view, it feels like your present choice is influencing what the particle did in the past. Retrocausality takes this idea seriously. It doesn't just say, "This looks weird." It says, maybe the particle's earlier state really is determined by something that happens later. Maybe causes don't always have to come before effects. Maybe time is more flexible than we think. Now, it's important to be clear here. Retrocausality doesn't mean you can send a message to yourself in the past or undo something that already happened. That would violate a lot of other rules in physics, and nobody's seen evidence for that kind of time travel. But it does suggest that the boundary between past and future isn't as sharp as we thought. In some interpretations of quantum mechanics, information flows both ways. What you do in the present can fill in missing pieces of the past. Not in a changing history kind of way, but in a completing the picture kind of way. This makes things complicated, because now you're dealing with a world where the full story of an event isn't finished, until both the beginning and the end are in place. It's like writing a book, where you don't know how chapter 1 works until you've already written chapter 10. There are real theories in quantum foundations that explore this idea. One is called the two-state vector formalism. It suggests that a quantum system isn't just defined by its state moving forward from the past. It's also influenced by a second wave function that comes backward from the future. The system is shaped by both boundary conditions, what was true at the beginning and what ends up being true at the end. That's a big shift in how we think. In most science, we explain things by looking at the past. If you want to know why the apple fell, you look at gravity and the tree and Newton's laws. You don't say, well, it fell because someone needed to eat it an hour later. But in a time-symmetric or retrocausal view of quantum mechanics, that kind of explanation might not be so crazy. Some physicists like this idea because it avoids some of the problems caused by measurement and collapse. Instead of imagining the wave function collapsing in one direction when we observe it, retrocausal models say that the past and future both help determine what we see. That way, there's no sudden jump, just a smooth combination of influences from both ends of the timeline. But this idea also creates its own set of problems. For one thing, it challenges our basic understanding of free will. If the future can influence the past, then maybe your choices aren't as free as you think. Maybe they're already baked into the full structure of space-time. That leads to another strange idea called the block universe, a view where time doesn't flow at all. Instead, the past, present, and future all exist together as one big, unchanging structure. You're not moving through time. You're just experiencing different slices of a fixed four-dimensional block. Some people find that comforting, others find it terrifying. What makes retrocausality even more interesting is that it doesn't actually break any of the math. Physicists have looked at this from multiple angles, and it turns out you can describe a lot of quantum phenomena just as well, or sometimes even more easily, if you allow future events to play a role in shaping what happens now. Still, not everyone agrees. Many scientists stick with interpretations that keep cause and effect moving in one direction. Others are more open to the idea that time might be an illusion, or at least a construct that only makes sense on large scales, not in the quantum world. And then there are those who think both views are wrong and we need a completely new way to describe how time actually works. Whatever the answer is, this part of quantum theory touches on something much deeper than just physics. It gets into how we experience reality. We're so used to thinking in terms of past and future, of before and after, of cause and effect. But quantum mechanics keeps throwing that logic into question. Retrocausality doesn't let us build time machines or rewrite history, but it does force us to reconsider the idea that time is a one-way street. Maybe it's more like a network of roads, some forward, some backward, all connected in ways we can't fully see yet. And if that's true, then the question isn't just what the past tells us about the future. It's also, what is the future trying to tell us about the past? One of the strangest things in quantum mechanics is how two systems, particles, devices, or even people, can seem to coordinate perfectly without ever exchanging a signal. No talking, no messaging, no way to share information. And yet, when you check their results, they're somehow in sync. Not just sometimes, every time. This strange behavior is often called quantum pseudo-telepathy. Let's break it down. Start by imagining a game. You and a friend are put in separate rooms. You can't talk to each other or send messages. Each of you will be asked one question, and you have to answer yes or no. The questions are chosen at random from a list. But here's the twist. If your answers match in a specific way, you both win. If they don't, you lose. It's a coordination game, but without communication. In the classical world, the best you can do is agree on a strategy ahead of time. Maybe you memorize a giant chart of possible question pairs and agree on how to answer each one. You can improve your chances, but you won't win every time. There will always be combinations you just can't handle without cheating. But now imagine you and your friend share a pair of entangled particles. These particles have a strange connection that doesn't depend on space or time. When you measure one, the other knows the result instantly, even if it's across the room or across the universe. Using that entanglement, you both make your choices based on your local measurements. You still don't talk to each other. You still have no way to share notes. But when the game is over and the answers are compared, they line up perfectly, in a way that no classical strategy could explain. That's what happens in quantum pseudo-telepathy games. Real experiments have shown that players using quantum entanglement can win games with a success rate that would be mathematically impossible using any normal method. No communication happens during the game, yet the results suggest something deeper is connecting the outcomes. The name pseudo-telepathy comes from this illusion. It feels like telepathy, like you're reading each other's minds or working together invisibly, but it's not. There's no message being sent, no hidden code. It's not even faster than light signaling, because nothing is actually being transferred between the players. The entangled systems are simply correlated in a way that makes classical logic break down. One of the most famous examples is the Magic Square game. It's a simple logic puzzle where two players must fill out a grid with ones and negative ones, following certain row and column rules. Without quantum mechanics, there's no way to win every round. But if the players share entangled particles and use quantum measurements, they can achieve perfect coordination. Not because they're cheating, but because the quantum world allows it. Another example is the GHZ game, named after the physicists Greenberger, Horn, and Zeilinger. In this setup, 3 players are involved. Again, no communication is allowed, and yet the players can produce answers that match in a way that no classical model can explain. This isn't just theory. It's been demonstrated in real labs. So what's really going on here? At the heart of it is quantum entanglement. When two particles are entangled, they're described by a single wave function. That means they're not separate objects with separate properties. They're part of one system. Even if you move them far apart, the system stays connected. Measure one, and you instantly know something about the other. Not because you sent a message, but because they were never truly independent to begin with. That's what Einstein called spooky action at a distance. He hated it. He thought it meant the theory was incomplete. But over time, experiments have shown that entanglement is real, and even stronger than anyone expected. What quantum pseudo-telepathy shows is that this connection isn't just weird, it can be used. It lets players do things that would be impossible otherwise, and it forces us to ask some uncomfortable questions. Is the universe really local? That is, can information only move through space at a limited speed, like light? Or is there something more going on beneath the surface? A hidden layer where space and distance don't matter? Is realism valid? Do things have properties even when we're not looking at them? Or do they only take on definite values when measured? These are deep questions, and quantum pseudo-telepathy sits right in the middle of them. It's not science fiction. It's not a trick. It's a real feature of the quantum world. One that seems to blur the line between what's separate and what's connected, between what's local and what's global. Some physicists try to explain it by saying the world is fundamentally non-local. Others think entanglement just reflects a kind of shared information that isn't bound by space. Still others say we need to rethink what we mean by reality in the first place. But no matter how you look at it, the fact remains. Two people can coordinate their answers without ever speaking, just by measuring quantum particles in the right way. It looks like telepathy. It feels like breaking the rules. But it's not. It's quantum mechanics. And the more you think about it, the more you realize how strange that is. Because if two people can act in perfect sync without sharing any information, what else might be connected in ways we can't see? There's a quantum experiment that sounds so ridiculous, it feels like a joke. Imagine you're watching a cat walk through a hallway, but instead of seeing the whole cat, you see the body go one way, and the grin go another. The grin floats off on its own, detached from the cat's face. That's the idea behind the quantum Cheshire Cat, a real experiment with real particles that seems to separate a particle from one of its properties. To understand how strange this is, let's talk about what the experiment is actually doing. In classical physics, when we talk about an object, its properties go wherever the object goes. If you take a spinning top and move it from one table to another, you don't expect its spin to stay behind. The spin goes with the top. Its position and its spin are part of the same thing. But in the quantum world, that assumption starts to fall apart. In the quantum Cheshire Cat experiment, scientists use neutrons, tiny particles that have both position and a property called spin. Spin isn't literal spinning like a top. It's more like a built-in quantum feature that helps describe the particle's behavior. It's important because spin determines how particles interact with magnetic fields and with each other. The experiment uses a device called an interferometer. This splits the path of the neutron into two possible routes, kind of like a fork in the road. The neutron is put into a superposition, which means it's not in just one path, it's in both at the same time until a measurement is made. So far, this is standard quantum weirdness. But here's where it gets strange. In the setup, scientists arrange the system so they can measure the position of the neutron in one arm of the interferometer and the spin in the other. What they find is that the neutron behaves as if it's traveling down one path, while its spin is detected on the other path. It's like the particle went left, but its spin went right. How can that make sense? It shouldn't. Not if you think of the neutron and its spin as one. In classical terms, that's like separating an object from its mass or separating heat from a flame. But in this experiment, The results suggest that the particle and one of its defining properties, its spin, can exist in different places at the same time. This isn't just a fluke or a mistake. The measurements are carefully designed. They involve what's called weak measurement, a method in quantum physics where you gather information about a system without fully collapsing its state. Instead of forcing the particle to choose a definite path or spin value, weak measurements let you get a soft, statistical hint of what's going on, without breaking the superposition completely. And when you collect enough of these weak measurements, a strange picture forms. One that says, the particle went this way, but its spin went that way. This is what scientists call a paradox. Not because they don't know how to describe it mathematically, but because it breaks our expectations about how the world should work. If a particle's properties can be separated from the particle itself, then what does it really mean for something to be an object? Is a neutron a physical thing traveling through space? Or is it just a collection of quantum properties that can drift apart and recombine? Some interpretations of quantum mechanics say this is just a measurement trick, that what we're seeing is not a literal separation, but an illusion caused by how we interact with the system. According to this view, nothing really splits. It just looks that way because of the probabilities involved. But others take it more seriously. They say this experiment shows that quantum systems don't have definite identities the way classical objects do. A particle is not a little ball with traits like position and spin glued to it. Instead, it's a kind of cloud of possibilities, and those possibilities can sometimes move separately. That has deep implications for how we understand what a particle is. If position and spin can be peeled apart, what other things can be separated? Can we split other properties? Can we extract charge without mass or energy without momentum? The quantum Cheshire Cat doesn't answer those questions, but it opens the door to asking them. It challenges our idea that physical things are solid, indivisible units. In the quantum world, that's not always true. It also makes us rethink the meaning of measurement. If what you observe depends on how and where you look, then reality becomes a kind of shifting story. One where objects don't exist in a fixed way, but take on meaning only when they're interacted with. This experiment also connects in a strange way to the Wigner's friend paradox. In both cases, the idea is that reality isn't just out there waiting to be discovered. Instead, it's created through interaction. The particle doesn't carry its properties around like a suitcase. Those properties unfold based on the context of the measurement. So, if you ever thought quantum mechanics couldn't get any weirder, just remember, there's a real experiment where a particle's property wandered off on its own, and the math and the measurements say that's completely fine. It's not just a metaphor. In the quantum world, you really can see the grin without the cat. There's one quantum thought experiment that pushes things beyond science and into something deeply personal. It's not just about particles or lab equipment. It's about consciousness, survival, and the strange possibility that from your point of view, you might never actually die. It's called the quantum suicide thought experiment, and it's based on one of the more extreme interpretations of quantum mechanics, the many worlds interpretation. The idea behind many worlds is simple but strange. Every time a quantum event happens, like a particle having multiple possible outcomes, the universe doesn't just choose one, it branches. All outcomes happen, but in separate versions of reality. So, instead of collapsing the wave function into one result, reality splits into all possible paths. You just happen to experience one of them. Now, here's where the twist comes in. Let's imagine a situation involving a quantum-based trigger, something that randomly results in one of two outcomes with equal probability. For example, a quantum gun that has a 50% chance of firing when you push a button, depending on the spin of a particle. The trigger is connected to a perfectly isolated box where no outside observer can interfere. Only the person inside knows what happened. Now suppose someone sits in this box and presses the button again and again. In half of the universes, the gun fires and that person dies. In the other half, they survive. But here's the strange part. From their point of view, their stream of consciousness, they always find themselves in the branch where they survive. Every time. It might be extremely unlikely, but there's always at least one branch where they're still alive. And their experience continues through that version. This leads to the concept of quantum immortality, the idea that your conscious experience can only ever continue in the universes where you survive, no matter how unlikely those outcomes are. To be clear, this isn't a claim that people can live forever in the everyday world. If you look at it from the outside, the person in the box dies in about half the experiments. That's what everyone else sees. But from the first-person perspective of the person inside, they never reach a point where their experience ends. They only keep waking up in the versions of reality where they're still alive. That's where the paradox lives, not in the mechanics of the experiment, but in the nature of consciousness. What does it mean to experience something if every possible version of you exists in some branch? What makes your stream of thought special? Why do you find yourself in this particular reality and not one of the others? The quantum suicide thought experiment doesn't rely on any new physics. It uses existing ideas in quantum theory, specifically many worlds, and asks what happens when you apply them to a conscious observer who faces death in one branch and survival in another. It's not a real experiment anyone can do, because it depends on subjective experience. But as a thought experiment, it raises questions that go beyond physics. One of the key issues here is the idea of observer selection. You can imagine billions of copies of yourself, all branching out in different directions with every quantum decision. But you don't experience all those copies. You only experience the one that lines up with your internal timeline, your memories, your thoughts, your awareness. That means survival. In this context, doesn't mean you live forever in the world that everyone else sees. It means that your inner experience never ends, because you're always in the branch where it continues. Now, that might sound appealing at first until you realize what it implies. It suggests that no matter how bad the odds, there will always be one universe where you barely make it through. Maybe you're the only survivor. Maybe you're injured or alone. Maybe everything else has fallen apart, but you're still here. That's not a happy ending. It's something else, something more uncomfortable. If your awareness always follows the surviving path, no matter how rare, you could be stuck in increasingly improbable situations. Every time you survive. But it might not feel like winning. From a physics perspective, this is just one interpretation among many. Not everyone accepts the many worlds view, and not all physicists agree that consciousness works this way. But it's a natural conclusion if you take many worlds seriously and ask how it applies to the observer. It also highlights how little we understand about the role of the observer in quantum mechanics. We can describe particles and probabilities, but we don't fully understand how observation works when it's tied to a conscious mind. Most interpretations try to avoid this issue or explain it away. But quantum suicide forces us to look directly at the connection between physics and subjectivity. That's why it's so powerful and so disturbing. It's not about changing the laws of physics or building machines. It's about asking, what is it that continues when everything else changes? What happens when physics meets personal experience? The quantum suicide paradox doesn't offer an answer. It just opens a door that most people didn't even know was there. And once you step through it, you can't help but wonder, is the version of me right now just the lucky one that made it this far? Out of all the places in the universe, black holes are probably the most mysterious. They're extreme in every way. Gravity, density, even time itself behaves differently near them. But beyond all the dramatic stuff like event horizons, black holes have quietly created one of the biggest paradoxes in theoretical physics. It's called the black hole information paradox, and it exposes a serious conflict between two of our best theories. general relativity and quantum mechanics. To understand the paradox, let's start with what a black hole actually is. When a massive star runs out of fuel, it can collapse under its own gravity. If the collapse is strong enough, all the matter gets squeezed into an incredibly small region called a singularity. Around it is the event horizon, the boundary where gravity is so strong that not even light can escape. Once something crosses that line, it's gone. You can't get it back. At least that's what general relativity says. It treats black holes as very simple objects. You can describe them using just a few properties: mass, charge, and spin. Everything else about what fell in, the shape of the star, the type of matter, the arrangement of atoms, gets lost. It's like the black hole forgets it ever happened. From the outside, all you can measure is a few basic numbers. Now here's the problem. In quantum mechanics, information can't just disappear. When something happens in a quantum system, the information about its state is always preserved, even if it gets scrambled or spread out. This isn't just a nice idea, it's a core principle. It's tied to how probability works in quantum theory. If information could be destroyed, the math wouldn't work. You couldn't trace outcomes backward, you'd lose predictability. So, what happens when you throw something into a black hole? General relativity says it vanishes. Quantum mechanics says the information must still exist somewhere. That's the paradox. The situation got even weirder in the 1970s, when Stephen Hawking discovered that black holes aren't completely black. Due to quantum effects near the event horizon, they slowly emit radiation, now called Hawking radiation. This radiation is very weak, but over an extremely long time, it causes the black hole to shrink. Eventually, it evaporates entirely. But here's the catch. Hawking radiation appears to be completely random. It doesn't carry any information about what fell into the black hole. So, if the black hole disappears and the information was never encoded in the radiation, where does the information go? It can't go into the singularity. It's cut off from the rest of the universe. It can't be in the radiation. Hawking's calculations say it's not. But quantum mechanics says it can't just be gone. So, something has to give. This isn't just a small detail. It's a fundamental clash between two major theories. General relativity explains gravity and the large-scale structure of the universe. Quantum mechanics explains everything on the smallest scales. Atoms, particles, forces, both work extremely well in their own domains. But when they're both needed at once, like near a black hole, they start to argue. And so far, we don't have a complete theory that can resolve the conflict. Over the years, there have been a lot of proposed solutions. Some physicists suggest that the information really is in the Hawking radiation. It's just very subtle, encoded in a complicated way that we don't fully understand yet. According to this idea, if you had perfect knowledge of the radiation, you could reconstruct everything that fell into the black hole. That would keep quantum mechanics intact, but it's hard to prove, because the decoding process would be incredibly complex. Another proposal is the holographic principle. This idea says that all the information about a three-dimensional region of space can be stored on its two-dimensional boundary, kind of like a hologram. Applied to black holes, it means that everything falling into the black hole gets stored at the event horizon. The horizon becomes a kind of information surface. As the black hole evaporates, the information leaks out slowly, hidden in the radiation. This idea grew out of string theory and has strong support in some parts of the physics community. Then there's the firewall paradox. This one suggests that if information is truly preserved, the region just outside the event horizon must be violently different from what general relativity predicts. Instead of falling in smoothly, anything approaching the horizon would hit a wall of high-energy particles, a firewall. That solves the information problem, but breaks a key principle of relativity, that falling into a black hole shouldn't feel any different until you reach the singularity. Each of these solutions comes with its own trade-offs. They try to fix the information problem, but end up breaking something else. That's what makes this paradox so powerful. It shows that we're missing a piece of the puzzle. Something big, maybe a new theory of gravity, maybe a better understanding of space and time, maybe even a new way of thinking about what information is. It's also worth pointing out that we can't directly test these ideas. We can't exactly throw objects into black holes and watch them evaporate over billions of years. But physicists are trying to find indirect ways, by looking at how entanglement works, or how information behaves in other extreme environments. Some researchers even study tiny black hole analogues in lab conditions, using things like Bose-Einstein condensates, just to see if similar principles apply. The black hole information paradox is one of those problems that seems simple at first. Where does the stuff go? But as soon as you try to answer it, you realize it touches everything. Quantum theory, gravity, time, causality, entropy, and even the nature of reality itself. That's why it's not just a problem about black holes. It's a problem about the universe. And until we can solve it, there's a limit to how much we truly understand. If you had to pick one thing at the heart of all quantum strangeness, it wouldn't be particles or equations or even time. It would be something much simpler: measurement. On the surface, measurement sounds straightforward. You look at something. You check its position, its speed, its state. But in quantum mechanics, measurement isn't just passive. It's not like checking the temperature or reading a clock. In the quantum world, the act of measuring something actually changes it. This is called the measurement problem, and it's one of the biggest open questions in all of physics. To understand the issue, you have to know what quantum mechanics says about particles before they're measured. Take an electron, for example. It doesn't have a single, well-defined position or speed until you measure it. Instead, it's described by a wave function, a mathematical object that represents a spread of possibilities. The electron isn't here or there. It's not in one state or another. It's in a combination of many states at once. That's called superposition. But the moment you perform a measurement, say checking where the electron is, you don't see a cloud of probabilities. You see one result, one position, one outcome. The wave function collapses, and the particle picks a side. Not because it was already there and you just didn't know, but because the act of measuring it forced it into one result. The problem is that the theory doesn't explain exactly how or why that collapse happens. The math tells you what the probabilities are and how the wave function evolves over time. But it says nothing about when or why those probabilities suddenly snap into one concrete outcome. That's the core of the measurement problem. What counts as a measurement? What causes a quantum system to collapse into one result instead of staying in superposition? There's no built-in rule in the equations that tells you when this happens. In a lab, we say the detector or the observer measured the system. But what actually changed? Did the wave function collapse just because a machine beeped? Or does it need a conscious observer? Or is collapse not real at all? Just an illusion we see when a quantum system interacts with something else? Over the years, physicists have come up with different interpretations to explain this. The Copenhagen interpretation, probably the most well-known, says that quantum systems don't have definite properties until they're observed. Measurement causes the collapse. But it never really defines what measurement means. It just says that something about the observer or the interaction forces the system to choose. Then there's the many worlds interpretation, which says the wave function never collapses. Instead, all possible outcomes happen, and each one branches off into a separate universe. In that case, measurement is just the point where your version of reality splits and you experience one of the branches. But that raises other questions. What determines which branch you experience? Why do you feel like only one outcome happened if all of them did? Another option is decoherence, which focuses on how quantum systems interact with their environment. It says that when a quantum object touches the larger world, air molecules, light, anything, it loses its quantum properties and starts to behave classically. The environment measures the system without needing a human or even a detector. But even decoherence doesn't fully solve the problem. It explains how interference disappears, but it doesn't explain why only one outcome becomes real to us. Then there's the objective collapse theories, which say that the wave function collapse isn't caused by measurement. It's a physical process that just happens, like radioactive decay. According to these models, large systems can't stay in superposition forever. Eventually, they collapse on their own. But no one has ever seen this happen directly, and the exact mechanism is still unclear. And finally, there's the more radical idea that consciousness itself plays a role, that a system collapses only when it's observed by a conscious mind. This is one of the most debated views, and it's often criticized for being too vague or philosophical. But it keeps coming up because nobody has found a better explanation for why reality becomes definite only when observed. No matter which interpretation you choose, the problem remains. We know quantum systems behave in strange ways before measurement. We know that after measurement, we get one clear result. But what turns one into the other? The measurement problem matters because it's not just a technical detail. It's about how we define reality. Is the world always there with fixed properties, even when we're not looking? Or is reality a process, something that only becomes real when it's observed? In classical physics, the observer is separate from the system. You can study a star, a planet, or a gas cloud without changing it. But in quantum mechanics, the line between the observer and the system becomes blurry. The very act of interacting with a particle changes what it is. That breaks the traditional idea of objectivity in science. This is why some physicists believe quantum mechanics is incomplete. Not because the math is wrong, it works incredibly well, but because it doesn't explain what's really happening underneath. It gives predictions, not reasons. It describes what we'll see, but not why we see it. And so the measurement problem remains unsolved, not because we haven't tried, but because every answer creates more questions. If measurement causes collapse, what counts as a measurement? If it doesn't, then why do we only see one result? If all outcomes exist, why do we experience only one? These aren't just technical issues. They're philosophical, foundational, and essential. Until we understand what measurement really means in quantum mechanics, we won't fully understand what quantum mechanics is even saying about the world. And maybe, just maybe, we won't fully understand what we are either. By now, after going through paradox after paradox, it's hard not to notice a pattern. Each one points to a different mystery. Some involve time, some involve observation, some involve space, causality, or information. But they all lead to the same uncomfortable place: the realization that our understanding of reality is still incomplete. Quantum mechanics is not just a strange corner of science. It's the foundation of how we describe the universe at its smallest scales. And it works. The predictions are accurate, the experiments repeat, we build technologies based on it, lasers, semiconductors, quantum computers. But when we ask what the theory really means, we start running into problems we can't answer. Every paradox we've looked at isn't just a quirk or an exception. It's a signpost pointing at something deeper, something that doesn't fit into the picture we've built. The quantum eraser shows us that time may not be one way. Wigner's friend suggests reality might not be the same for everyone. Retrocausality challenges the very idea of cause and effect. Pseudo-telepathy and entanglement expose a kind of connection between things that shouldn't be connected. And experiments like the quantum Cheshire Cat blur the boundary between a thing and its properties. Then you have thought experiments like quantum suicide, which don't just question what happens to particles, but what happens to us. And the black hole information paradox reveals how two of our most powerful theories, quantum mechanics and general relativity, are speaking different languages. They don't just disagree on details, they fundamentally don't line up. At the center of all this sits the measurement problem, reminding us that we still don't know what turns possibility into reality. We can calculate probabilities, predict distributions, and describe superpositions. But we can't explain how or why one specific outcome appears when we look. Put all this together, and you get something more than just a list of scientific puzzles. You get a clear message. Our current picture of reality is likely not the final one. That doesn't mean quantum mechanics is wrong, it's not. But it might be incomplete. Or it might be telling us something we haven't learned how to hear yet. The mathematics gives us the how, but we're still missing the why. And that gap matters, because it affects more than just experiments and equations. It affects how we think about existence itself. Are we living in a world that exists independently of us, where everything happens according to fixed laws? Or are we part of a reality that is, at some level, shaped by our interaction with it? That question isn't just philosophical, it's practical. If observation plays a role in shaping outcomes, then understanding the observer becomes part of the science, not as a mystical idea, but as a necessary part of the model. Maybe consciousness isn't just along for the ride, maybe it's part of how reality gets written. Of course, not everyone agrees on that. Physicists are divided. Some believe all these paradoxes will disappear when we discover a deeper, cleaner theory that ties quantum mechanics and gravity together. Others think the paradoxes are clues that we need a new way to think about physics entirely, one that doesn't rely on fixed space, linear time, or even objective reality. There's also a growing recognition that we might be approaching the limits of what our current tools can explain. Not because the universe is hiding from us, but because we're still trying to describe it using ideas that were built for a simpler world. Newton's universe was mechanical. Einstein's was geometric. Quantum mechanics gave us a probabilistic world. But perhaps the next step is something even more abstract. Maybe the universe isn't made of particles, fields, or even space-time, but something else we haven't quite named yet. And this is why paradoxes are so important. They're not flaws, they're guideposts. They tell us exactly where to look. They mark the boundaries of what we understand, and the places where something new might be waiting. Some of the biggest breakthroughs in physics started with paradoxes. Newton's laws came out of questions about planetary motion. Relativity came from inconsistencies in electromagnetism. Quantum theory itself was born when classical physics couldn't explain blackbody radiation or the photoelectric effect. Each time, the paradox wasn't a mistake. It was the key to a bigger, more accurate theory. So maybe we're standing at the edge of something like that again. A new kind of physics that explains why the quantum world looks the way it does, not just mathematically, but meaningfully. A theory that connects all the weird pieces. Superposition, entanglement, non-locality, time loops, black holes, and the role of the observer. We don't know what that theory will look like. Maybe it's buried in string theory. Maybe it's in the math of quantum gravity. Maybe it's something no one has even thought of yet. But if it exists, it will have to explain why the universe behaves the way it does, not just how. Until then, we're left with a model that works beautifully, but leaves us full of questions. Questions about reality, identity, observation, and time. Questions that science alone may not be able to answer, at least not yet. And maybe that's the most honest place to end. Not with answers, but with awareness. That no matter how much we've learned, we're still staring into the unknown. Still chasing something just out of reach. Still trying to figure out if the universe is real, or just responding to the fact that we're watching.